students, welcome back. Spring break happened. Are you happy with spring break? Yeah, you like break, huh? Break is good. Break's good for all of us. I hear there was a basketball game a couple days ago that was... I had Virginia as my top team. Actually, what's funny about that, I have... So I'm part of two bracket pools, right? And so the model kind of gives me these statistics that do things, and then I sort of tweak off of that when I put my bracket in. And so one bracket pool is with my some colleagues up in EPSY. And I have 3 of the 4 Final Four teams. I have Villanova, Kansas, and Michigan. And the other one I was invited to be part of with some colleagues in the field of mine that I don't really know that well, so it was like, nervous. But I think what it's going to come down to is if Kansas beats Villanova on Saturday, then I win. But if Villanova beats Kansas, then I'll come in like 3rd or 4th place. So it's one of those things. So we'll see what happens. So I'm rooting for Kansas for a number of reasons. Neither of these have money involved that I'm going to be taking because I don't gamble on this stuff for that reason. But it's been pretty exciting, huh? Yeah, it's a good thing class wasn't yesterday. Maybe liver one day a break. Anyway, hope you don't mind. I took my daughter who lives in Tuscaloosa likes to Snapchat. That's her way to communicate with me. So I decided to take a picture of the class quickly and send it over. But hopefully that won't bother anybody. So might send me do that. A couple other housekeeping notes before break. There were a couple videos I posted on YouTube. Do you remember those? Vaguely. Yeah, so that's where we're going with things. These are videos that are involving kind of introduction to multivariate linear models, absolute fit, and robust maximum likelihood. Not exactly riveting stuff, I know, but stuff to move us into a spot where we're going to be actually doing some multivariate stuff, and today we're going to continue with that, so it'll refresh your memory. There was no quiz today, so everybody's happy about that, right? But next week there will be a quiz because just before class, I put up another video for path analysis. Hooray! Maybe. I don't know. The quiz will be simple, don't worry, I promise. Like usual, when we did have quizzes. Way back when. The other thing to note is homework 4 is now available. I got that up today too. Hooray, hooray. We'll talk about that at the end of today, but it's going to be related to what we're talking about today. But there is a part of homework 4. You remember GLHT, the thing you've had to use in like the first 2 homeworks? Where we use a package named Lavon now. Lavon doesn't work with GLHT, but what it does actually do is let you capture all of the parameters by labels you can give them, and you put the labels into a function. So you'll need that to do your homework, and that actually is described at the end of the path analysis lecture. So just a heads up on that. Other questions? Homework 4 is due April 9th, which is a Monday. It's actually fewer questions this time than before. There are 22 computational questions, 15 results questions. So it's not a huge homework, but it still will be expected to be. I'm trying to minimize where the hassle is going to be rather than just overwhelm you on every possible region. So it'll hopefully be a challenge, but at the same time, it'll be, once you get into it, it'll hopefully be much more familiar because it's going to be like linear regression again. Just now we have 2 predicting variables. The other thing with that is homework 5 is actually going to be the same thing as homework 4. But we're not going to do that with Lavon. We're going to do that with the mixed model package, Elmer, LME4, linear mixed effects models package. So the reason why I do that will become much more discussed as we go along. But generally speaking, there's these big camps of people in multivariate statistics. They come from different disciplines, and they do things in different ways because of parts that somewhat become important whenever you get a certain reviewer or something else. And so I want to show you each way because that might be the way you go forward with a lot of things. Okay. Any other questions for me? It's good to see you. And those of you who are online, it's good to be heard by you. I think that's what he'd say. I'm not sure that you can ping me otherwise. I don't know. Maybe you can find my number to text me. Nope, my ringer's off. Never mind. I don't know that you can find me. Okay. So today we have a lecture, mainly because of our sort of backup of things. I tell you, the next version of this class will be better. I hope it's at least you're getting something from it now. It's really hard. It's been very hard for me to develop the lectures, record the lectures, and develop the homework all simultaneously. So that's why we've sort of had things staggered. So I'm sort of taking the long view, which is I'm hoping I'm giving you things that help you with what your programs of studies are and get you prepared for whatever you might do next. But it's not as cohesive as it will be if I did this multiple times this way. So that's sort of where it goes. But our lecture today is the multivariate linear models with predictors. We do have an R syntax file as well if you'd like to see it. Again, we're going to use Lavon, so I'm going to talk about all the fun things that go with Lavon as we go forward. And if you haven't watched the videos online, cool, you'll hear some of it here, but I would really encourage you to watch those videos online because it kind of gives you a little bit more of the startup for things. Okay, everybody looks like, gosh, here we go again, right? Sorry. You know there's only like 6 more meetings. If you count today, there's only 6 more meetings of this class, which I was like, that seems unnecessarily long. But only 5 after today, which is better, right? I kind of wanted that to be like 4, but yeah. So I'm going to keep trying to give you some more content. Yeah, but the iPad decided it does not want to actually make this work. That's right. Oh, that's right. Hang on, make sure. Whenever I do that, it crashes my OBS, but I think it's working. Yep, I'm recording. There we go. So I'm not going to use the iPad, and I'm just going to share this with you as not a slideshow, because there's no way to eject out of, or to start a slideshow in a Mac. At least I haven't found. Maybe you have found this. If you're using PowerPoint on a Mac, you can't easily start up not in slideshow or presenter mode when you have 2 monitors, right? If you know that. Anyway, yeah, that's, if you're on Windows, it works, but okay, so we're going to talk a little bit more about multivariate linear models, but now we're going to add predictors. The things online were just multivariate linear models using empty models. The empty models were there to try to tie what we're doing with multivariate models to that multivariate normal distribution. Let's back up. Remember multivariate normal? No. Remember univariate normal? The bell curve? Multivariate is univariate in multiple dimensions, right? And every time that you do, in a multivariate model, the hard part that you have to face is that, bless you, for every variable you add, in the distribution, you add, essentially a mean and a variance, right? So every variable gets those, but you also add a covariance with all the other variables that were there before. And so that means, I think I said this on those lectures, there was the curse of dimensionality. Ever heard that term before? It's actually a Wikipedia page for it, I think. Hold on, let's see if I can do this. Look up curse of dimensionality.
Here's some information.
That's it, look at that, it's from Wikipedia. It's not just me, if you don't trust me, if it's got a Wikipedia page, right? What more do you need? A Facebook page? No, that's not. That's kind of going out of style. Yeah, some propaganda about it? I don't know. Never mind. But generally speaking, it is the idea that the one of the complicating factors of going from one variable to multiple variables in a linear model sense is that you have a lot more things that you have to worry about. That hits us in the multivariate world in 2 ways. Number one, we have to estimate all those things potentially, which means the more parameters we have to estimate, the harder it is to have good power for all the effects that we want to have. Right? The other part we have to worry about is model fit, right? Because if we don't estimate all those parameters, what we need to have is a model that fits just as good as a model with all the parameters. But one that works well. I'm looking at my typos. There's a typo there. Aper. Anyway, so don't do this while drinking. Anyway, so we're going to talk a little bit about some more stuff that comes on in this as we go through it. I had a long time ago, when I did my first multivariate class at Georgia, I had a path analysis lecture, and I was like, I need some data. Let me see if I can find some on the internet. So I just Googled path analysis in education, and this is the first scientific article that came up, and I'm like, I know David Miller, I'll take it. And so I took it, and I was like, well, let me just generate the data. So I've been using these data for years now, and you'll be sick of it. And so now, we're using this for, how many lectures now? I talked about it just an hour ago in path analysis. So it seems very familiar, but just to talk about it with you directly here, 10%, so this is supposed to mirror a sample of 350 undergraduates, proportionally almost 2 times as many women than men. This is from 1994, by the way. And about 10% of the variables were missing, and so I just randomly deleted those. And you'll note, once again, if you see result differences between what we have in class here and what you may read in that paper, which you can find online as well, it's not necessarily, don't take that as a put down of the paper or a put down of the method. It's just because I generated data under the assumptions of multivariate normal, whereas not all the data that they have fit that assumption well, right? Some of those are bounded, some of those have other issues. And actually they're, all the continuous variables have the multivariate normal distribution. But you'll see in my data, some of the simulated data exceeds where the boundary is supposed to be, like the performance variable is supposed to do the number of items correct on an 18-item test, and the number that you may see there might be negative, it may be positive. It's just how generating data from chance works. Okay, questions? All right, I should mention once again, the plan for today is for me to lecture with breaks. By the end of the class, we will have, hopefully in the last half hour or so, I'll introduce the homework, give you a good way to set it up. And then next week will be a more traditional work on your homework or work on R after a little bit of time discussing things and questions you might have, okay? Excellent. Scattered today. Yeah, 6 weeks left, gosh. So here are the variables in the data example. Today we're only going to use only several of them, really. We have a sex variable, and actually this has been driving me nuts since I generated the data. I think one of the tables in the paper actually reported one of the signs wrong, because some of the effects are very interestingly opposite from what I expected and what I do, and so I'm just going to label the first variable as female, so meaning people who are female, biological sex, have a 1, otherwise male 0. So male is the reference group in this case. Math self-efficacy, we're going to use perceived math performance. That's reported an AT item. So basically the students in this study filled out a bunch of surveys and then had to take a math test. Talk about one of those awesome SONA experiments, right? So our SONA coordinator for EPSY, one of our SONA coordinators. So we, you imagine doing that? Have you all done studies in your student history? You ever signed up for one where all you do is fill out surveys, and then at the end of that you got a math test? Woo! That's the one that like when the year runs up and you're like really trying to get your credit, you're like, all right, I'll have to do it. That one. So there's 18 items. The other variable we're going to use is a self-reported scale that's something about the perceived usefulness of mathematics. It's sort of trying to indicate how well you perceive mathematics will be useful in your life. Interestingly enough, if I was an undergraduate, I probably would have rated that very lowly my first semester, but then I took statistics and I was like, whoa, really useful. And thankfully, it helps pay the bills now. I will also note, I've said this online, but I'm going to keep repeating myself here just to give you multiple exposures. The reliabilities of these instruments are not one. All right? That's a problem, because what we're doing in statistics assumes all of our variables are perfectly reliable. So if you have a situation like this, and you're using not perfectly reliable variables, a couple things happen to your effects that we know pretty demonstrably happen. Number one is that your beta weights get shrunken. Right? They essentially get smaller than they should be. But number two, the standard errors for those beta weights get a lot smaller than they should be. Right? So you think about what that means, right? So now all of a sudden you're saying, well, okay, so the strength of the relationship isn't that strong, right? But what happens, what do we do with the standard error? Do you remember the Wald test? I'll just put it out there, forget that. Remember the Wald test? How we evaluate whether a parameter is significant is we take the parameter and divide it by its standard error. Right? So the numerator of that's getting smaller, but if you have not perfect reliability, then the denominator gets smaller. So what wins? And I've seen a few papers, it's not widely talked about, but I've certainly seen it in simulation studies where it tends to lead to a lot of type 1 error rate issues. The standard error gets much smaller than we expect it to be, and that's because when your reliability is 0.93, you have a lot more information, or not 1, or 0.788, which is really not good. You have a lot more information. The model thinks you have a lot more information than you really do. And so it's effectively adding things. So I think that this is one of the bigger issues that we face in a lot of social and educational science work, is that if you have measured variables that aren't perfectly reliable, that you might start to see type 1 error issues. If you see type 1 error issues, that starts to get into a little bit of a problem with reproducibility of results. Because if you have a spurious, you may have more likely of having spurious findings in your research. And some of the fields where we have the biggest problems, particularly fields like social psychology. Anybody love social psychology here? Justin. All right. Well, I won't. It's not a bad field. Not bad, but no. Oftentimes you take a survey and you do something to it, and do something to it, and do something to it, and each time you've got a little bit of error with it, it adds up, and next thing you know, you start to see findings that look like they're real results, but might be spurious. And so I'm telling you this because we're not going to be able to address that in this class. But if you want to address that, that's a good place for you to take a structural equation modeling class. And next semester, we do have one, EPSY 906. I think I sent you a note about Lisa Hoffman is teaching that, but she has, you can enroll, you send her a note, an email, and she'll send you a survey. She tries to, she only has so many spots because everybody has a computer in class. She hasn't gone laptops like all of us here. So she tries to limit, if class gets impacted, which it hasn't really for her for a couple of years, but she tries to give it to people who are later in their programs of study and, trying to be somewhat fair. 24 spots. So if you want to do that, take her class, which is pretty cool, or maybe pretty cool. So anyway, this is the path model that showed up in the paper that I talked about. The path model itself, I'm going to let you watch the slides, watch the video between now and next week describing what all this means in a big picture sense. I'm going to talk about it in a small picture sense when we go forward, but this is where we're going, and this is what you'll see when you get there. And part of that is because I just got done talking about this, and now I am lecturing again. So my selfish reason. But the big picture of what we're doing is that we're going to model multiple variables simultaneously. Right? So we have multiple regression equations all at once. Now, there is a benefit to having multiple equations in a model in that if you have a correlation between those variables, you get to share information across the regression. Right? So you may be able to enhance power if there's things going on in certain ways with some types of analysis like this. But in that, just let's go through it. We're going to take those variables and we're going to pretend they're multivariate normal. We're going to use the conditional multivariate normal. After we've predicted things, the errors are multivariate normal. Which means we have to talk about mean vectors, right? The set of means. And covariance matrices, right? Bless you. Covariance is the redheaded stepbrother of correlation. Remember that? A correlation goes from 0 to 1, or -1 to 1. The covariance is bounded, but it's bounded by the variances that are with the respective variables. So covariance is important. But when we do this multiple simultaneous regression equations, what ends up happening is that without even making an attempt to do so, implies that our data should have a covariance matrix that's very specifically shaped, specifically formed. Right? So it's a little bit weird to think about, but think of it this way. You can collect data, easily. Well, I don't know. I always like to say, if you're collecting your own data, any data is big data, right? It all takes a long time. But let's just imagine you have someone else's data that they collected for you and whatnot. You can get a covariance matrix from that. That's sort of our standard for what our model should look like. Right? Our model should resemble the data. When we fit a multivariate model, depending on some of the ways we specify it, it may be the case that our model looks nothing like the data. Right? And one way that we can summarize it is the model itself has a model implied covariance matrix. And we can easily take that model implied covariance matrix and compare it with our data covariance matrix. And what we should see if the model fits the data is they should look similar. Right? They should be in big in the same places and small in the same places, and they should have roughly the same values. So the key in multivariate models is to find a good approximation to that covariance matrix in our data. Now, covariance matrix in our data goes by the term unstructured or saturated, meaning we estimate, if you were to estimate all the covariances, just all of them all at once, right, you would be looking at the covariance matrix from your data, right? That's an estimate. So we want to make sure our model looks like it, if possible, with as few parameters as we need. Right? So maybe some of those variables, some of those covariances are redundant. Maybe they're the same. Maybe some are zero. Right? We want to build a model that does that with as few parameters as possible, and mainly because the parameters cost us power, cost money, cost time, effort, people. So there's a little bit of an art to these multivariate linear models in that you want to specify them in ways that guarantee you have a good shot at getting that covariance matrix right. Sound good? So what I just said, if you do anything with factor analysis, anything with classical test theory, you've taken 822 or 822 is one of our classes, 725 is one of our classes, 921, these are all EPSY classes that do it. You are actually in specifying a model that whole field sort of stopped being a field around 1950. I don't know why we're still teaching it, but the topic. That field doesn't really understand very well, but sure enough, it has ramifications for what you do. So why I'm telling you this is if you do take another class, particularly one in measurement, if you're doing things with scales, you're doing a multivariate model for your data for the most part, even if you don't realize it. And being off has big ramifications. One of those, very big one. How many of you have taken data from a scale? Forget you. How many people do you know of or read a study of? I've done this before, but let's not point fingers here. But if you take data, if you created a scale, an instrument, a test, and you sum up the number of items, how do you compute the reliability of that test? Do you remember? Or heard of it or learned it? What is reliability? Well, the reliability is effectively how consistent scores would be if you were to give the test multiple times and sort of wipe the mind clean for a person. And one of the ways that we can talk about reliability is something sometimes people call Cronbach's alpha. You've heard of that? Cronbach's alpha, believe it or not, was not really first invented by Cronbach. So it sort of makes me go, ugh. It was Gutman who did. Some people call it the Gutman-Cronbach alpha. But sure enough, that reliability will likely be way too high if your model does not resemble the data. Right? And so a lot of what you'll learn in kind of the early measurement classes that we have, although again there's 3 of them and there's one at 7, 8, and 900 level classes, you can learn how to compute that reliability, but you never learn how to assess whether or not the model fits the data. And that's where you have to take a multivariate class or whatever else. That's sort of one of my pet peeves. So yeah, that's a big thing I want to get across. Reliability is not model fit, it's a consequence of it. Just like the parameters that you get from your analysis are not really valid potentially unless your model fits the data well. So just think about that in the back of your mind. Oh my goodness, have I checked the model fit even if I add up a bunch of variables? Yes. So we're going to talk about some of these models that work that way. I'm preaching today. It's just, I don't know where this is coming from, these impromptu lectures. Maybe it's because the echo when I hear myself talk in here makes me seem like I have this big audience of like half full room or less than half full room. I don't know. So we're going to do multivariate linear models via path analysis software and packages. So that's really nuanced there. Multivariate linear model, meaning we're going to do multiple regression lines all at once. Path analysis software is the package Lavon. Similar to Lavon, Lavon is sort of built off of a bigger package that costs a lot of money, something called M+. So much so the people who do M+ really hate the people who develop in Lavon, at least I've heard. I don't know, respectively. But there are other ones out there. Lizrel was one of the very first ones. You may have heard that before. EQS might be one that came along in the 80s as well, and there's variants that show up in, Amos in SPSS. Stata has a package now that does it. So they show up all over the place. But this is one way of doing multivariate linear models. I'm starting here first because I believe it to be a little bit more understandable to learn at first. Because when we get to the next one, it's sort of like jumping into the deep end. And I'd rather just sort of get you familiar with it. Yes?
SPSS. Mm-hmm. So if we use SPSS, we can to analyze multivariate statistics with them?
Yeah, of course you can, but you may not want to. Very limited, yeah. Yeah, I don't know. Honestly, I don't know. I don't. The thing I like to tell people is I don't even have it installed on my computer, so I don't know. But yeah, in theory, you might be able to, depending on what you're doing. Each of the packages give you a little bit different numbers, which is somewhat unnerving. But yes, there's a package. It's not SPSS itself, but SPSS has a program that it used to install when I did install it on my computer called Amos. Does it still get installed? Does anyone know? So that's the part of SPSS that does this. And it should get fairly consistent numbers with Lavon, although where things start to get a little weird is what happens when you have missing data. It's what happens when, what assumptions the program is making about the model underneath the hood sometimes impact the results a little bit differently. But that's SPSS can do this in Amos. Sorry, I will not be teaching you that though, but I'm sure there are some great people on YouTube that'll help. Yes, Mary Beth.
I'm trying to find the slide. Is it the introduction?
Let me find out. It will be under multivariate linear models. In-class materials, it would be, so under multivariate, the March 27th, under in-class materials, yeah. Nope, no problem. I've got too much, there's just too much stuff on the website anyway, so glad you asked. Thank you. Other questions or thoughts? Okay. By the way, break at 2:20 and 3:20, all right? So just, if you're wondering, or you're welcome to leave the class at any point in time. There's no penalty. You don't need to raise your hand. It's totally cool. We're all adults. But just so if you want to plan when you want to go, there's 2:20. I know I've screwed up once or twice this semester with break, and it was sort of that, how much am I going to lecture impromptu? And I just have too much rambling, too much comes out. I need to learn to be quiet. But 2:20, okay? Okay, let's start with multivariate regression. Okay. In the lectures online, we had performance and usefulness, and we used a multivariate empty model to model those. The multivariate empty model just had an intercept and an error term for each of these regression equations. When you have an empty model in multivariate statistics, the same thing works that you have when you have an empty model with a univariate, with a single regression, in that the intercept represents the mean of that variable. The error will have a residual variance, and that sure enough will be the variance of your data. And you could have a covariance between the two variables now, right? So all of that will look like your data if you do that. It'll fit your data perfectly, actually. The other part with that is that you'll note that the parameters get a little bit more confusing because now we have to denote which intercept is which, right? Because we have more than two variables. Each variable is going to have an intercept. So this beta 0 now has another subscript to it describing which variable it's the intercept of. Right, so beta 0 perf represents the intercept for the performance variable. Beta 0 use represents the intercept for the usefulness variable. We need those to denote each other differently because the syntax, the notation for it's a little bit different. Now in the output from the computer, it'll Clearly, there'll be a section that says intercept, and you'll see each of the variables there, but that's how to think about these. What we're going to do is, to our empty model, add 3 variables. We're going to add whether or not the indicator variable of a person being a female, or the sex variable here, for each of those lines. We're going to add the variable CC, which stands for, I believe, college credit hours, the number of credit hours in mathematics a person took in college. And then just to show that we can do it, we're going to add the interaction between the sex variable and CC, because the homework that you're going to have will have this in it. I want it to be a little bit more representative. But then when we get to path analysis, sometimes interactions go away. Each one of these equations works the same way as it would work as if it were a univariate linear model, right? You can specify interactions between any variables. You can specify main effects between the variables. You do all the same things you do with each regression equation. It's just now there's 2 of them. The other thing I'll note is it's not necessary, although in this example we have the same predictors of each of the same dependent variables. You don't have to do it that way, right? It may be the case that you wouldn't expect college credit to predict performance. I don't know why that would be. Maybe a college credit to predict usefulness, right? Maybe that's it. I don't know why that would be the case, but the point of the matter is you can specify the model separately for each of these variables as if it were a separate linear regression altogether. Cool? Yes. No, no problem. That's right. That's right. So we have 2 dependent variables. Performance is one of those. Remember, performance is the number of items correct out of 18 on that math test. And usefulness is a score of some point from the survey for the usefulness variables. That's right. Now the main effects, again, because the beta weights that go with each of the dependent variables are not going to be estimated to be the same unless we force them to, which topic for another day. We don't need to do that right now. So because of that, we need to denote that they are different. That's why you see the way I tried to, the syntax is clunky after a while. I can never get something I really enjoy. But here, the first subscript on a beta represents the thing it's multiplying. So in this case, the main effect of being female. And the thing after the comma represents the dependent variable that's on, right? So when I look at these 2 pieces of notation, I see that the female variable is a predictor in both of our linear regressions, but that we would expect to have different main effects for either of them, right? So we'd estimate a separate main effect for one for performance and one for usefulness. That's why there's a different notation. Does that make sense? Becomes just a lot more problematic. This set of slides, I think PowerPoint crapped out on it because it's 15 megabytes. They get really heavy really quickly in the Word and the Office suite when you try to add in equations to it. So I hope that, does that make sense? Okay, other questions? Okay. The other thing I'll note is those 2 error terms. Before we used to say that, in a univariate linear regression, we'd say one error follows a normal distribution and it's got some type of residual or error variance to it. But now because we have 2 of them, that's where this multivariate normal distribution comes in. That's why I spent the time trying to tell you about multivariate normal a little bit ahead of time, just to not be too weirded out by it. Just like before, each of the errors means, respectively, is supposed to be 0. Right? So we sort of set that by default. In a linear regression, our residual or error term had a mean of 0. In the multivariate linear regression, both error terms, means, are 0. But now, because there's 2 of them, we have a covariance matrix that represent the variances and the covariance between them. So what this term right here in the diagonal is sigma squared error underscore error comma performance. That's the residual variance for performance by itself. That says that sort of what's left over after we account for predicting performance with our main effects, or predictors. Main effects interactions. Does that make sense? So it's what we saw before. Still down the diagonal of this matrix, the sigma squared error for usefulness represents the residual variance of usefulness, just like we saw before. If we were to use usefulness as a univariate linear model, right? So it's what's left over, the variance left over after we account for each of the predictors as well. So the only term that really is different in this analysis from that univariate model is sigma squared error, this thing in the off-diagonal, the covariance, or what we would call the residual covariance between performance and usefulness. Now, what is that thing? That's weird. But let's think, hear me out here. Our estimate of error, if you remember where that, if we were to try to find that, what we would do is we'd create a predicted value for each person based on what we call the model for the means. And the difference between the predicted value and the model for the means would be error, right? That's how we'd find error. So if you imagine for each person in our sample, we created error in that way for both performance and for usefulness, right? So we've got these two error terms now. If you were to put a scatter plot of those together, you might see a correlation between the two, or a covariance, right? And that's what this term is supposed to capture. It's supposed to identify and quantify how related the errors are for usefulness and performance. Because what that might help with is it sort of provides a connection between the two analyses themselves that actually does impact, it may provide better estimates of the variables in the analysis. If they're highly correlated, that sort of, you borrow information from one regression to the other. It's one of the benefits of the multivariate analysis simultaneously. So it's an odd term to think about. It's sort of a nuisance, to be honest with you. We often don't think very highly of it. You ever heard that term in statistics, nuisance parameters? People do call them that. This is sort of a nuisance. It's like, yeah, I probably should floss. No, I shouldn't say that. That's gross, right? I floss every day, thank you. Just kidding. Try to make you, I don't want to make you too grossed out. The statistics is already bad enough. Dentist is bad enough. It's like, I don't know what a good nuisance is, but something that's there, right? I should probably worry about that. Ryan.
If the error, like, my understanding of error is supposed to be, I guess because we're looking at variance, it's supposed to be random, right?
That's right.
If the errors are correlated, is that saying that some part of the error is not random?
Yeah, essentially, because we have two errors now in this multivariate model, we're saying that those errors may be somehow related, particularly because each observation is coming from the same person. Our model may be off in the same way for these variables, in one way or the other, that causes them to be the error to be correlated. But I'm making a big deal of this now because that's the one distinction between multivariate and univariate that changes. Most of the time in life, you will never do anything with that term. You'll see it. Sometimes you may add it to a model to make it fit better. But rarely do you see it interpreted and rarely do you see it used. So just remember that. But that's the big distinction between the two. Cool? Other questions? All right. So we're going to, here is a histogram, by the way, of college experience. And we're going to center college experience at 10, which is, I believe, the median. 10 credit hours of math in college. That's what we're trying to center it at, right? So now the 0 point is 10, and that's because we have an interaction with college experience there. And 0 means something for the interaction variable, right? Or main effects in the presence of the interaction. Okay, so, yes?
Even though 0 means something, this one is actually still centering?
Absolutely. Well, sorry, we're trying to make 0 mean something.
Oh.
I mean, we could say a person with 0 credits of math in college. I know for us at this university, well, we have undergraduate requirements of math, at least some credit hours. And so it's unrealistic to think of a person who has absolutely 0. I mean, I guess it could happen. There's all sorts of ways, as I've learned in the university. As you get your PhD, it's like, oh, there's all these other hoops to jump through and all these special caveats. Like the rest of the university world is nothing but that too, right? So there's got to be ways of people saying, no, I have 0. But let's think of, what I want to do is make it a little bit more meaningful. So I'm going to put it right in the middle of the distribution. So maybe the median person's number of credit hours. Okay, yes, 0. You have 0? You had 0, see, it's possible. It's possible. Is that at Georgia? No. No. Never mind. It is possible. So a couple things now start to come into play when we have predictors in the analysis. And there's a distinction made between the type of variable that you see. This comes up more in path analysis in the next lecture that you'll watch online than it comes up for us today, but we're going to talk about it now because it's a little bit more simple with just a handful of variables. The distinction, why do I say extinction? My son asked me first thing this morning, Dad, were dinosaurs real? He's 3, right? So I'm like, yeah, but they're not real anymore, right? So maybe that's it. I don't know. The distinction is that a variable is either classified as endogenous or exogenous. Kind of an odd way of putting it, but endogenous variables are variables who have variability explained in the model. So what do I mean by that? If you're a dependent variable, you're an endogenous variable. So everything to this point, in linear regression, everything we've ever done has one endogenous variable. For our analysis right now, we actually have 2, because we have performance that we're predicting, so that variance gets explained, and we have usefulness that we're predicting, so that variance gets explained. Now again, endogenous and exogenous variables for this type of multivariate regression is pretty ridiculous. They're pretty limited because you look at the number of DVs you have, you say those are all of my endogenous variables. You look at all the predictors you have. The opposite of endogenous is exogenous predictors. Right? The predictors you have in a model are exogenous variables. Those are variables that vary, that may even co-vary, but we're not making any effort to explain why their variance happens. We're just saying it does. Right? So in our case, there's variation in who's a female. Yes, absolutely. We see sex differences, right? Biological sex differences between people. We're not going to explain it. In fact, explaining it would probably be very difficult. It's rare that you see a variable characterizing biological sex as a dependent variable, right? What predicts what sex a person's going to be, right? That's hard to do. Again, it's certainly different for gender identity, but for sex, the chromosomal, right, the actual sex differences, not likely you'll find it as something you're predicting. College experience. We're just saying, yes, people vary in their amount of college experience in mathematics. We're not going to explain why. It just happens. Right? We're going to use that to explain why people vary in math performance. Or we're going to use those variables to explain why people vary in mathematics usefulness. So in linear regression, the independent variables are always the exogenous variables. Where it starts to get crazy is something like this. What these lines, these arrows represent is whenever you see a box, that means a variable. Whenever you see a box with an arrow at it, it's like saying high school math experience is being predicted by the thing that's on the other side of the arrow, or sex. So now all of a sudden, high school math experience, its variance is being explained, or trying to be explained, by sex. So it's endogenous. But now we also see that high school math experience predicts mathematics performance. So we have endogenous variables that predict other endogenous variables. Now what do you do with that thing, right? So that's where we'll get, the answer is once endogenous, always endogenous, right? And so that's where I get the distinction. How do I decide between endogenous and exogenous? As I like to think is an endogenous variable is inside of the model, right? Like these things are kind of here that have the arrows that terminate to them are in the model. I don't know if that makes much sense, but that's sort of what I describe it as. So when you look at a path diagram like this, when you look at a picture of what's going on, we're trying to describe a lot of models all at once. You can tell the exogenous variables by whatever notation is being used to denote a residual variance. And so in this graph, each of these blue lines says these are the things where we're explaining variance. Residual variance is variance explained. It's what's left over after the regression. So in looking at this path model right now, apart from the whole parts that we haven't gotten to yet, we can see right now there are 6 blue paths, so we would expect there would be 6 regression lines specified in this analysis, right? And using the distinction of endogenous versus exogenous, every time there's a blue dotted line, that means an endogenous variable, means there's 6 of them. We see that sex does not have a blue line to it. That means it's exogenous. So that's how we make that distinction. Why that distinction becomes important, particularly when we get to path analysis, is we use it to understand whether we have too many things going on in our analysis, too many parameters in the model. Because it's possible you can overload things to the point where it won't work. Now, it's sort of extreme, so don't worry about that yet. You'll see it in the slides coming up. But that counting, we remedy that by counting. I know it sounds really ridiculous, but it helps us understand what's endogenous and exogenous for counting. I'm getting ahead of myself. So here is the path diagram for our multivariate linear regression. Here we have our variables performance and usefulness. They have blue dotted lines. They represent endogenous variables. And you may see that this is supposed to be a double-headed arrow there. That looks like a double-headed arrow more. This term right here is the covariance between the two. So when you see a single-headed arrow, that means a direct effect or something unique. When you see a double-headed arrow, that means there's a covariance there between the two variables. Okay. So that's on the right-hand side. On the left-hand side, we have female college math experience. And I actually create a brand new variable, female by college math experience. This is the literal product of F times CC. Because in an interaction, in moderation, that's really what you're doing. You're creating a brand new variable that's the product of the two before it. So that's where you see them. Now, the orange lines are sort of denoting that these things have variances and covariances, but we're not going to describe them. They're not being explained by anything. They just exist. So those are exogenous variances and covariances that are in orange. And then what's in the middle represent our direct effects. So we're saying that mathematics performance is being predicted by female, by college math experience, and by female by college math. And each of those arrows are trying to represent the slope for each of those variables. Okay, so that first arrow represents the main effect of female and predicting performance. This slope right here represents the main effect of college math experience predicting performance, and this last slope right here represents the interaction, it's down here, of female by college math experience predicting performance. This is how we disentangle it. What's missing from this graph? Path diagrams are great in some respects and bad in others. Because a path diagram quickly tells you what's happening in a model with the direct effects, what's showing up, what we would call just our beta weights, our parameters, but you don't see all of them there. And what's missing is every variable's intercept. We don't have an intercept for performance or usefulness shown here. We don't have a mean shown for female college math experience or their interaction. No, direct effects are any prediction. And actually, that's a really good question because in the path analysis lecture, we're going to contrast direct effects with something called an indirect effect. The direct effect is literally when you see a variable predicting so for each endogenous or dependent variable in your model, when you have a variable that's predicting it, that's called a direct effect. Right? So in this case, each one of our predictors is a direct effect. Direct effects include the main effects, include the interactions. So that's part of what happens. You cannot see it in this analysis, but if I were to tell you it with the big picture, it is possible in path diagrams, I know it's 2:20, actually I've got 1 minute. In path diagrams, it is possible to think about the indirect effect, which really gets into the world of mediation. What an indirect effect is like the following. Let's imagine high school math experience. We can see it has a direct effect on college math experience. And if we go back to what linear regression tells us that direct effect means, it says for every 1 unit high school math goes up, the college math experience changes by its beta weight. And for simplicity, let's just say it goes up. You take more math in high school, you take more math in college. Again, this is 1994, by the way, so these days I think everybody's taking all the math they can in high school. It's not something that you get that choice to. I don't remember I think I could have gotten rid of math in high school, but I just chose to fail it. So your generation is far better than mine. This high school math experience has a direct effect on math self-efficacy as well. But now take a look at what happens. High school math experience may have an indirect effect on math self-efficacy. And what do I mean by that? Think of it this way. High school math experience, when it goes up 1 unit, when a person takes one more class in high school, we know college math experience goes up by beta units. Right? So those beta units that college math experience goes up, guess what happens? If there's a direct effect of college math experience on mathematical self-efficacy, math self-efficacy might increase by that proportionally, right? And so that's the distinction between a direct effect and an indirect effect. The direct effect shows up specifically on each endogenous or dependent variable's line of the model, the regression line, whereas the indirect effect has to come from multiple models to provide that for you. So thank you for the question. That's a very good one. I'll take other questions after. Let's take a break for 10 minutes, and I'm a minute late. I apologize, and we'll come back and have some more fun with this.